the uses, applications of radioactivity. We already know what radioactivity is and which elements are radioactive. And beside this, we studied about parent nuclei, daughter nuclei, types of radiations, alpha, beta, gamma, and their penetration power, their ionization capacity. All these we have already studied in the face-to-face classes. And we studied briefly about the uses of or applications of nuclear radiations. Okay, so here we have some specification of the topics. Like here, what is to be studied? Describe the uses of radioactivity in medical and non-medical tracers, in radiotherapy, and in the radioactive dating of the archaeological specimens and rocks. And you can describe what dangers ionizing radiations may cause. Like radiations can cause mutation in the living organisms. Radiations can damage cells and tissues. They can cause problems, different problems, the problems arising in the disposal of radioactive waste, and describe how the associated risk can be reduced, how to minimize, how can we keep ourselves safe from the harmful effect of these radiations. So, radiotherapy. Here, high doses of radiations can cause the normal functioning of the living cells to change, and this can lead to abnormal growth and cancer. So, very high doses will kill the cells. It means this part, that is, high doses can kill the cells. We can use for curing different diseases. We can kill the cancerous cells, etc. Okay, but we have to keep the healthy tissues safe. We have to shield the healthy tissues so that they remain safe from the harmful effect of those radiations. Here gamma rays treatment is shown here. The gamma rays camera is to be there, but person has to be given some drink, and that can be monitored from the outside. Why a gamma is to be used? Because beta and alpha cannot pass through the body of the person, so they cannot be recorded by that camera. Okay, so they can be administered externally. Okay, so using gamma rays, or internally can also be done, but we have to use some chemicals that emit alpha, beta, or gamma radiations. Okay, that is in chemotherapy. Here, radioactive tracers are used to follow the flow of substance through the body, and they can be monitored from outside of the body. Okay, so here the gamma camera shown opposite can show where a patient has absorbed a tiny amount of radioactive substance. So, like iodine is absorbed in the thyroid cells. So, if a person is given a drink, so it will be absorbed more in the thyroid cells. And when it is examined from the outside using GM tube or a gamma ray camera, then that part can be seen, because this part will be emitting more radiations. Okay, so doctors can tell using seeing this image, they can tell how the particular part or particular organs are functioning. Then what kind of source should be used for that purpose? There are the properties. The source must emit gamma. Why gamma? Because alpha or beta would not be able to pass out of the patient's body to the camera. The source must have a long enough half-life to remain reasonably active over the period of observation. It means it should not have too short half-life that the job is not done properly, and that count rate or disintegration rate is decreased, and it's not of any more use. So in the half-life of that source should be long enough, but it should not be that long that it remains harmful in the body even after completing the job. Okay, when the purpose is done, that the half life, like it should have decayed almost completely, or the radiation rate should have decreased, that its presence in the body causes no harm to the person. Okay, should not be too long, that it does not irradiate the patient's body for a longer than needed. Okay, the radioactive substance must not be toxic nor decay into the substance that is toxic or radioactive. Okay, that is also a very important point, because if the radioactive source which is used in the patient's body, whether it is implanted or it is given in the form of a drink, then of course it will decay into any other substance. So that substance in which it decays, it should be non-radioactive. Okay, otherwise it will also have another half-life period, and it will also be emitting radiations for another period of time. So that should not be there. The isotope which is used for that purpose should disintegrate into a new compound, new atom, which is stable and does not decay more. So isotopes used include iodine 131 and 123. Half life of 123 is 13 hours. 131 has half life of 8 days. Okay, so different substances are used. Here there is another one, technetium 99. It's an isotope and its half life is 6 hours. So where very short half life period is needed, this technetium 99 can be used, and for the little longer period we can use iodine 131, which decays into half in 8 days. Another use tracing underground leaks in the pipe. So here this is the GM tube which is monitoring from the outside, and this is the pipe which has some leaks. So in order to high level of radioactivity means presence of leakage. So suppose here the amount of radiation emitted is higher. Okay, means there is a leakage present in this area. Okay, here the amount of radiations which is received is less. Okay, so it means the water which flows into the pipes, that should be that should have some radioactive substance to be added, and that will be emitting radiations. So what kind of source is to be used and what should be the half life? Let us see. The radioactive tracer can be added to a fluid, okay, which will be flowing through this pipe like water. Where a leak occurs will be shown by an increase in the count rate. Okay, so when we detect more count rate, it means the leakage is present at that part. Okay, properties of the source, it should be beta. Alpha will not be able to pass through the ground above the pipe. Okay, gamma radiations would give the same count rate whether or not a leak was present, but depends upon the type of pipe also. Okay, like if the pipe is made up of thick iron or some other material, then gamma can also be used. Okay, and half life again should be long enough so that we can find out the fault. Okay, and it should remain active only for that period of time. Okay, again half life should not be that long that it causes hazard to the environment, because of course the radiations will enter the environment, so its presence should not be for that longer period of time. Now here are some questions, the blanks to be filled in from these words. A radioactive dash can be used to detect leakage in the underground pipe. A radioactive, what comes in this? Let's see. Tracer can be used to detect leakage in the underground pipes. Beta source is added to the liquid being transported by the pipe. The ground around the leak will therefore become radioactive. The source must produce beta radiation because alpha radiations would not be able to penetrate through the ground. Okay, the dash of the half-life of the source must be long enough for it to remain detectable, but not too long as to cause long-term radioactivity in the ground. Sterilization. Another use, microorganisms on medical instruments such as plastic syringes can be killed using a strongly ionizing source of radiations, and we call it sterilization. We can use UV rays also for this purpose, but radioactivity can also be use. This process can be used on medical instruments while they are still within their packaging. Okay, when they are in the package, we can irradiate them with some radioactive source. Okay, and we can use these radiations to increase the lifetime of food, and that means for the food preservation. Okay, so in the market, different foods are available which are preserved. Okay, so they are preserved usually by using some chemicals, or they are preserved by using this radioactivity. Okay, again, quality control, automatic thickness monitoring. So this is aluminum foil which is to be prepared of uniform thickness. So how the thickness can be maintained? This is passing, coming out of the, you can say, where they are made, okay, and they pass through this beta emitter, and a detector is there on the other side, and this is aluminum foil. So if this is thick at any point, the computer will order the roller to press the aluminum foil. So then when it's pressed and the required thickness is achieved. Amount of radiation received by the detectors depends on the thickness of the foil. So if the thickness increases, then the detector reading will fall. Of course, few particles, few radiations will be received at the detector. If the thickness is less, it is required thickness, then constant amount of radiations will be received at the detector. But if the thickness is increased, the count reading will decrease. And computer will of course function at that time. It will get the instructions, it will and these instructions will be passed on to the rollers, and these rollers will decrease the thickness by pressing it. Now what type of source is used here? Source is beta because aluminum foil it is. Alpha would not pass through the thinnest aluminum foil. Okay, gamma would not be affected by the thickness changes, because in order to stop gamma we need thick lead sheet, okay, and long half life. Otherwise you will have to replace the source. If the source is having shorter half life, then it will finish and it will not be able to do its job anymore. So it means the half life should be long, and again, and false thickness will false thickness increase will be detected as the activity of the source decreases. Okay, because if half life is short, then the activity will decrease. What is activity? Activity means radiations emitted per unit time. Okay, so if the half life is long, the amount of radiations which are emitted by the source, they will almost remain same for longer time. If half life is short, means the amount of radiations per unit time which are emitted by the source will decrease quickly. Okay, so we will not be able to monitor the thickness properly, because that decrease in the count rate either is due to change in the thickness, or due to the change in the amount of radioactive atoms present in the source. Okay, so that is very important, that the source should be able to produce constant amount of radiation for longer time. If the short half life is there, then this source will decay quickly, and amount of radiations which are emitted out of the source will be decreased. So that will get wrong reading, whether this decrease in the count rate or in the detector's reading is either due to decrease in the count rate, or it is due to the increase in the thickness. So we cannot monitor this. So that is why this should be having, the source should have longer half life, so that activity will remain same for longer time. Another use, smoke detector. They look like this, and they have alpha. Why alpha? Because alpha are good at ionizing the air. Okay, so inside the gap, there will be some radioactive source, and that source is usually alpha emitter, and it will conduct electricity. In the next slide, you will see the diagram. In a fire, smoke prevents. If in a fire, smoke prevents the radiation causing ionization. The drop in the electric current caused sets off the alarm. Alarm will be turned off. Okay, when the current is dropped. Why the current will be dropped? Because the smoke will prevent the radiations causing the ionization. Okay, so here this is the gap, alpha particles, and this is the plate, and when the current is decreased, the alarm will sound. Properties required of the source. Alpha and beta will not cause enough ionization. Okay, so they will not be affected by smoke also, because ionizations are very small, because gamma or beta, they are not good at ionizing. Their ionization capacity is weaker than alpha, and again long life, half life, so that we don't need to replace it uh, after a short time. Okay, they can be used for longer time. And alpha, because they have low penetration power, so if the source is mounted on the roof or on the ceiling, that will not reach the ground. This will not cause harm to the people who are living in the room or in the area. Okay, and these are the source. Americium 241 alpha emitter, and half life is 433 years. So it means this activity will remain constant over a long period of time. Another use of radioactivity, dating. Okay, we studied in the live classes, in the face-to-face classes, about the carbon dating and carbon 14, which is used to find out the age of dead organic matter. Okay, so here there are some examples, and uranium can also be used to find out the age of depending on how old a material is. Okay, we can use uranium, we can use carbon, and beside this we can use some other radioactive elements. So here living materials, for example plant, contains a known tiny proportion of radioactive carbon 14. This isotope is produced when high speed neutrons part of the cosmic radiations. What are the cosmic radiations? They enter our atmosphere from the outer space. Okay, so these neutrons, they collide with the nitrogen and they produce carbon 14. Here is equation. This neutron, which reacts with the normal nitrogen, when it reacts with the normal nitrogen, it produces radioactive carbon. Okay, it's another isotope. Normal carbon, stable carbon is carbon 12, and this is radioactive carbon. Okay, and one proton is released in this reaction. So carbon 14 decays by beta emission back to the stable nitrogen. Okay, within half-life of 5,600 years. Okay, so it will be this carbon 14, it decays and again becomes nitrogen and it emits beta particle. So carbon 14 is chemically identical to this normal carbon, which is non-radioactive. Plants absorb carbon 14 during the process of photosynthesis. So all living materials will contain certain proportion of carbon 14, as will any animals that eat these plants. Okay, it means from the plants, this goes into the body of the animals also. When a plant or animals dies, it no longer absorbs any more carbon 14, and this carbon 14, it keeps on disintegrating, its amount keeps on decreasing. Okay, so fresh piece of any plant or fresh piece of any or newly dead material will have greater amount of radiations emitted out by that carbon 14 beta radiations. Okay, but then old plant will have a small amount, because when activity depends upon the number of carbon 14 atoms present. So fresh plants will have, of course, more carbon 14s, and dead plant, because carbon 14 decays, so number of carbon 14 atom will be less in a dead material. So how much less depends on how long ago that plant or animal died. Okay, so the age of one's living material can be estimated by comparing its residual radioactive carbon content with the living material. Again, we have to take care, the quantity, the sample should be same, and the amount which we take for testing, it should also be same. So limitations of radioactive dating. Radiocarbon dating process assumes that the level of cosmic radiation reaching the Earth is constant, and this can be corrected by using objects of known age, such as mummies of the Egyptian pharaohs and the no longer living parts of ancient living trees. And again, carbon dating is can be used for the dead organisms whose lives are of about 60,000 years. More than that, carbon 14 will not be able to give exact reading. Okay, that means we'll have to use some other material whose half life is longer than 5,600 years. Okay, because in 60,000, how many half lives of the carbon 14 will be there? 10 half lives. So here is an example. 360 gram of living wood has an activity of 72 becquerel. Becquerel is the unit, and you can call it disintegration per minute or per second. Okay, so count per second. Becquerel means count per second after deducting background radiation. So it means the background radiation is minused from this. A 360-gram sample of wood from an archaeological site is found to have an activity of 9 becquerel. Okay, so living wood has greater disintegration rate because it has more amount of carbon 14, and dead organic matter has 9 becquerel only. So estimate the age of the wood if the carbon 14 has half life of 5,600 years. So we can check how many half lives would have passed. We can check after one half life, the radiations will remain 36. Half of 72 is 36. Okay, half of another half life, and this is one half life, this is second half life, 36, half of 36, 18, and after 18, 9. So it means 1, 2, 3 half lives have passed. So one half lifetime is 5,600 years, 3 half lifetimes is this. Dating rocks. There are a number of techniques that involve comparing the relative proportions of the elements found in the rock samples. When formed, the rock may contain a radioactive isotope such as uranium-238, and this is parent nuclei. Okay, and it decays into thorium-234, which itself decays into other materials, and finally it becomes lead-206. 200, this is stable isotope of this lead, and it is daughter now. Okay, the older the rock sample, the greater will be the lead 206, because this will keep on decaying, uranium will keep on decaying, and in number of stages it will form lead. So the older one will have more amount of lead. So this uranium can be used to find out the age of the Earth because its half-life is longer. Half-lives in the table below give the time taken for half of the parent nuclei to decay into the final stable daughter nuclei. So these are the half-lives of different uranium-238, 235, thorium-232. So they have very long half-life period. So they can be used to find out the age of the Earth also. Okay. So now here, another radioactive material which can be used is potassium-40, because this has half-life of 1.25 billion years. So that is also used to, like where carbon 14 does not work, we can use this potassium-40. Carbon 14, if it's not able to do the purpose, we prefer potassium-40 here. So a non-porous sample of igneous rock contains 3 times as much argon 40 as potassium 40. It means argon 40 is daughter, okay, and its quantity is 3 times greater than the potassium 40. Okay, estimate the age of this rock. Initially, it means it had only, suppose, potassium 40. We will assume here, and as the time passes, argon 40s are formed, and we have to find out the age of the rock, and like after that age, after that time, the argon 40 is 3 times the potassium 40. Let's see how it's solved. assuming that the rock was formed without any argon 40. We have just made our calculation simpler by assuming that in the beginning there was no argon 40 element. Okay, after one half life, 1.25 billion years, there would be 50% of argon. Half of them will be argon, half of them will be potassium. Okay, 50%. Now half of left over, that means half of this 50% means 25%. Okay, two half lives, there will be 25% potassium and 25% argon, and if we add that 25% argon to 50% argon, total is 75% argon, and now 75 is now 3 times greater. It means how many half lives have passed? 2 half lives. So it means how many years? 2 times 1.25 means 2.5 billion years have passed, and now the proportion is what? This quantity is 3 times, argon 40 is 3 times greater than potassium 40. Hazards of nuclear radiations. These ionization caused by radiations can damage or kill the living cells. They can cause their mutation, they can cause genetic mutation, etc. Alpha particles cause the greatest amount of ionization and are therefore potentially the most dangerous type of radiations. But we can shield against them easily because they can be stopped simply by paper. So what are the safety precautions? The main precaution is to reduce the dosage received to the minimum possible. To achieve this, radioactive source should be stored in a lead-lined container, be handled for the minimum possible time with the tongs, never pointed at anyone, never be put in the pockets, be checked, and can never be checked by, and it has to be checked by looking at them in the mirror. You don't have to look directly into them. Okay. Problems with the nuclear waste. So when nuclear reactions take place, like fission reaction, the waste products, they should be deposited safely. Okay, so nuclear waste is radioactive and it may have to be stored safely for thousands of years. Okay, the waste is stored under the ground in sealed containers that must be capable of containing the radioactivity for thousands of years. Suitable sites also must be found free of the effects of earthquakes or groundwater leakage. That has to be taken care of again. Okay, now the spaces to be filled in, radioactivity can be used to date the material. Radiocarbon dating uses proportion of radioactive carbon 14 to the stable carbon 12 in a former living sample. Rocks can be dated using parent isotope uranium 238 and its stable daughter isotope, that is lead 206. Radioactivity causes ionization, which can cause living cells to undergo genetic mutation, leading on to possibly cancerous growth. It is therefore important to minimize exposure, especially to alpha particles, which cause the most intense ionization. Now there are some questions to be answered. See them, do them, and watch the video again when you have any queries and ask me in the face-to-face classes. Allah Hafiz.